Hello, this video will be explaining problem number 14 in chapter 4. We'll start with the free body diagram. Oh, looks like I'm still set on purple. Okay, so start with the free body diagram. You have a force going down. I don't even remember what the question is now. Let's see. Oh, the thief one. Okay, so we're doing the one where the person is trying to escape from prison. It's not something I recommend you helping anyone attempt. But we have a force of gravity acting on the person going down. We'll have a force of tension going up. And there is a positive direction going up as far as I'm going to label it. And you have the mass of the man, which I'm just going to write AN, so the word spells man. It's going to be 75 kilograms. And the maximum mass that the person can, or not the person, that the rope can hold is 58 kilograms. So that's going to be important information. The person is obviously going to be closest center of the Earth, so the acceleration is going to be 9.8 meters per second squared. And we're trying to figure out how the person can get down the rope without it breaking from a 3-story building. Okay, so now some of you guys would be thinking, okay, we just get 2 ropes or fold the rope, which would work. You are correct about that, but the only problem is that the person's in jail, doesn't want to stay in jail any longer than they have to. So and materials would be scarce, so they're looking to get out as soon as possible with the materials they have. So yes, there are other options if they stayed, but you can actually go down the rope and leave the jail with what materials are already provided, as long as the person accelerates when they go down that rope. If the person has an acceleration in this direction, that means there's less force acting on the rope. Okay, so we can go ahead and say we know we're looking for an acceleration. We don't know what that acceleration is yet, but if we can find it, we can figure out how to help them escape. Or for example, if this was a scenario for security, you can go, okay, we need to make sure that they don't have any ropes to escape prison with. So before we can start, we need to identify the forces involved. We're going to write Ft max because that's actually the maximum force of tension. It's not going to be any other numbers. We want to know, well, what's the acceleration of the man if he's putting the maximum force. I don't want A there, I want G. So before you can do that, you need to figure out, well, what is the maximum force of tension? Well, the maximum force of tension would be the weight of the 58 kilogram person. Okay, so we can really just say Ft max would equal the maximum mass times G. And you actually see these kinds of problems a lot in engineering, where you're always trying to find out, well, what's the maximum load a building can take or a structure can take. So when you're doing that, if you're using a maximum mass, you're also using you're finding a maximum force. Or in most cases with engineering, you are calculating the maximum mass. The maximum mass find from the force. Like they tell you, okay, this piece of steel can take this much force, and you have to then figure out, well, how many occupants can take up the building. Or in some cases, it would limit the amount of furniture that you can put on in a building. A lot of people don't think about that, but that's definitely a common problem. I had to do with those problems in some of the architecture classes. So just keep that in mind. Sometimes you're given a maximum force and you can figure out what's the maximum mass that can be occupied in the space. And other times in this scenario, we're told the maximum mass, we can find out the force it can withstand. Now we can go ahead and have the maximum mass was 58 kilograms times the 9.8 meters per second squared. So you get the maximum force of tension to equal 568.4 newtons. We don't round the number because it's not actually the number we're looking for. And now we can use that value back here, so we can go ahead and try to figure out, well, what would the sum of the forces be. Now you need to remember the sum of the forces will equal, so force divided by mass will equal the acceleration. And so if we just multiply the mass over, we can go ahead and substitute out the sum of the forces. So that's what I'm going to do. We're going to have sum of the forces divided by the mass, and I'm going to write the mass of the man just to be clear that we know what we're doing there, will equal the acceleration of the man. So if we go ahead and say we substitute it out for the sum of the forces, we just have the mass of the man times the acceleration of the man equals Ft max minus, and Fg is just another way of saying the mass of the man times the acceleration of gravity. So we can isolate, divide the mass of the man over to the right. We have the acceleration of the man equals the maximum force of tension minus the mass of the man times the acceleration due to gravity, all divided by the mass of the man. You would have Ft max is 568.4 newtons. You would add that to 75 kilograms, because that's the mass of the man. And wait, it shouldn't be added. Sorry, I added on accident. It should be minus 75 kilograms times 9.8 meters per second squared. Yeah, and then divided by 75 kilograms. You should get the acceleration of the man equals a negative 2.2 meters per second squared with sig figs. Let's see, 75 times 9. Yeah, okay, that looks good. So if the person accelerates down the rope at a rate of 2.2 meters per second squared, he will be able to reach the bottom without the rope breaking. Now, to help you understand this, it does not mean the person will go down with a velocity of 2.2 meters per second. Okay, a lot of people think that for some reason the acceleration is explaining the speed that they're going down, and it's not. It's the change in velocity. So that means the person has to keep going faster and faster while going down. To help you visualize this, it'd be as though he loosely holds onto the rope, and as he jumps off the building, his hands start to slowly let go of the rope more and more until the point where he's barely touching the rope and he's accelerating well, I may not be barely touching the rope, but he's not touching the rope nearly as much as he was before, and he's accelerating down at a rate of a negative, or down, so at a rate of 2.2 meters per second squared. So about a fifth of the acceleration of gravity. Okay, keep in mind, if it was an acceleration that would be dangerous, he could, based on the distance he's falling, once he gets close enough to the bottom, he could start to close his fingers around the rope again. It would obviously increase the force acting on the rope, and the rope would snap, but it would cause him to slow down slightly right before the drop, or right before landing, so that could save him possibly from injuring his legs. Um, but that's not really part of the problem. But it is something you could keep in mind, that you could always squeeze the rope once you get towards the bottom to slow down, but it'd only be for a moment due to the maximum force that the rope can hold.